Let's let X represent a female college student's weight measured in pounds. And let's assume that we know that the population mean weight for these college students is 140 pounds with a standard deviation of 26 pounds. So typically, the weight of female students is normally distributed, meaning that we can expect that most female college students will have weights that are similar to each other. So their weight is going to hover around the mean of 140 pounds. And then, of course, there are going to be some female college students who weigh more, some who weigh less than that mean value. All right, and those who are very heavy, okay, they're not going to be as many, so the frequency gets lower. And then those who are very, very light, okay, below the mean weight of 140 pounds. They exist, but again, not at a high frequency. We expect most female students to kind of have the same weight, which hovers around that mean value. Okay, now let's take a look at a question like question A in your homework problem. In a question like A, this is where we are asking a question like, what is the probability that if I randomly select one female college student, that her weight is going to be between 125 pounds and let's say 145 pounds. Now, my drawing is not drawn to scale, but this question is saying, let's take a look at this distribution of x's, right, where each x represents the weight of one female college student. I want to know, what are my chances that the x that I choose is going to be between 125 pounds and 145 pounds. So if I take a look at this distribution and shade in the area that contains all the weights that are between 125 and 145 pounds, I hope you can see that those are the x's that are in that green shaded area. So what are my chances that I picked one of those x's? I can calculate that probability by using my calculator. So if I want to answer this question, I can use that function called normal CDF. Okay, normal CDF for normal continuous density function. And that function is going to ask us to put in our lower bound, which will be 125. Our upper bound is going to be 145 pounds. And then we're going to type in the mean and the standard deviation of this distribution, which is 140 and 26 pounds. So I'll let you put that into your calculator and figure out what that probability is. But it's going to be an answer that's going to be between 0 and 1. Okay, let's move on to a question like question B. Now, a question like question B, we are no longer looking at the distribution of a single value, which is like the distribution that I just drew on the left here. In a question like B, now we're asking ourselves, what is the probability that if I randomly select, let's say, 4 college students, right? What if I randomly select 4 X's? What's the probability that the average, so X bar, the average of those 4 weights is between 125 and 145 pounds? Can you see the difference between a question like A versus a question like B? So in question B, again, we're saying, what if I randomly select 4 x's? Maybe it's this x here, this x there, this x here, and that x there. If I take those 4 female college students' weight and average it together, what would that average be? Okay, and what if I were to repeat this process many, many times, where every single time I keep picking 4 random x's, so 4 random female college students' weight, and then calculate the average. So if I were to do that, I'd be able to create another distribution where this distribution contains a bunch of x bar values, where every single x bar represents the sample mean, or the average of my sample of 4 female college students' weights. So again, we have to apply the central limit theorem here. The central limit theorem says when I take the average of all of these x bar values, the mean of this distribution is equal to the population mean. And the standard deviation of this distribution is equal to the population standard deviation divided by the square root of n. So again, that is the central limit theorem. So to answer a question like B, right, I can also use my calculator function, normal CDF. I'm kind of running out of room here, so I'll squeeze it I'll do it on the left here. So on my calculator, I can use normal CDF, okay? My lower limit will still be 125. So here, on this distribution, I can mark 125 and 145 to be somewhere there because I know that at the center, the mean of this sampling distribution is the same as the population mean of 140. Again, my drawing's not drawn to scale. And I want to know what are my chances that I pick an X bar value, so a sample mean value that's in this green shaded region, okay? So I can use the same bound. So on the left here again, let's put in our lower bound of 125, our upper bound of 145. And then here, I would have to put in the mean of the sampling distribution. But again, the central limit theorem says that that's the same as the population mean. So I can also type in 140. And the key difference here is the last thing that I type in, I have to type in the standard deviation of this distribution. And the central limit theorem tells me that that value is the population standard deviation divided by the square root of my sample size. So now you can put this into your calculator and see what that probability is. And that probability is going to be the shaded area that we have on this distribution on the right. The last question, a question like question C is saying, right? Question like C. So question C is saying, notice that our sample size is really small. 4 is really small. And what's considered small is a sample size that is less than 30. So question 4 says, why are we allowed to use normal CDF? So why are we still allowed to take a look at these bell-shaped curves when our sample size is so small? And the answer to that question is, if we know that the X bar values, okay, are averages that come from us pulling X's from a distribution that's already normally distributed. So we know that weights of female college students is already normally distributed. When I pull from a population that is already normally distributed, I can get away with smaller sample sizes. So I hope this helps.